Hello everyone, welcome to today's talk. I'm Dong. Today I'm going to talk about the temperature-dependent electrical resistivity due to magnetic impurity, aka the Kondo effect. So this is our outline. We'll first talk about the Kondo effect reduction, and then we'll go deep into the Green's function study. After that, we get the result. We'll compare between the model and the experimental data. And then we will discuss one interesting universality of the temperature dependent of resistivity, and furthermore the future of the Kondo physics nowadays. First of all, what is Kondo effect? So Kondo effect is a scattering process between the conduction electron in the metal and the magnetic impurity on the metal. So it will result in a characteristic change in the electrical resistivity with temperature. This was raised by Jun Kondo in 1950s, and according to the experiment we can see here, this is the data taken from the gold metal with little iron impurity, which serves as magnetic impurity. And we can see a resistance minimum at the finite low temperature. People usually think that the resistivity should decrease monotonically as the temperature decreases. But then this mysterious minimum raises. And hopefully after today's talk we'll be able to answer why there exists such a minimum at finite low temperature. Before we go into the Hamiltonian of Kondo effect, these two slides I just made it like 3 hours ago, and the reason I made these is because one of my friends told me like Philip Anderson died on March 29th, which he is a great scientist. You might know him, just he wrote The More is Different, the emergency phenomena, and Mona showed us in his lecture Physics 502. And he is also a Nobel winner at 1977. His Nobel Prize, work is actually pretty related to what we are talking about today. So he talked about the local moment and the localized states, where he used the so-called Anderson Hamiltonian to picture this local moment in the metal. Both Anderson Hamiltonian and the Kondo Hamiltonian, which we will discuss later, reproduce the Kondo ln 1/T result. It's kind of interesting that in his talk he mentioned neither Kondo nor Anderson model behaves reasonably well at the low temperature, more specifically saying T below the TK is a T Kondo. Don't be afraid about the Kondo temperature, we will mention it later. But I just want you to keep this question in mind so that later hopefully we can answer this one. So for the Green's function study of the Kondo Hamiltonian, we have our ground state Hamiltonian as the Fermi C, and for the perturbative Hamiltonian we have minus J as dotted with the local density operator of the conduction electron. We can then split this S into SZ and S plus and S minus operators, and we call this first part as the Ising part because it's proportional to SZ, and the second part is spin flipping because it consists of S plus and S minus. Just give you idea why there will be spin flipping here. Consider our system, we have our impurity atom in between of the Fermi C. So for this electron sitting here at this orbital, there will be probability that this electron will tunnel through the barrier and go onto this Fermi C and forms a virtual state. And then there will be electron from the Fermi C that tunnel back to this orbital. But this electron could have spin up or spin down. If this electron hop back to this impurity orbital is spin down, then we get a final state is a spin up state in the Fermi sea, while in the initial state we have spin down. So this is a spin flipping process. Then we use the single electron Green's function here to be our initial Green's function, and we have our Hamiltonian H1 here. So our goal is to obtain the T matrix expansion of this scattering process. We'll follow the usual step as we did in the lattice distortion phonon case, where we use the Feynman-Dyson expansion to expand the Green's function in the power of H1, and we use Wick's theorem to solve this expansion, while in the end Feynman diagram to pick up the non-trivial terms. But there does not exist a Wick's theorem, conventional Wick's theorem for the spin operator, unless we can convert it back into the quasi-particle pictures, just like what we did in the lattice distortion case, where we convert the lattice distortion into the phonon. Luckily, there exists a fermion-drone representation of the spin operator. It is as follows. So because we are utilizing a quasi-particle picture, we first have two fermionic operators C and D defined in the usual way, and we can reconstruct our SZ S plus S minus operator into the C and D operators. So apart from C, which is Sion, our first quasi-particle, we have the second quasi-particle, which is Dion, defined as D dagger plus D is equal to phi. And with this, you can also check like the spin operator actually preserves its commutation relations. Then we can write down our Hamiltonian with the quasi-particles. It's like this. After that, we can calculate the propagators correspond to Sion, Dion, and spin flipping part. They're as follows. We can also draw their, because we later will draw the Feynman diagram, so we will represent them into lines. So the wiggle line is the Sion, and the dot line is the Dion, while this, there's a loop here, which is one Dion and one Sion, is our spin flipping part. And the last one is our usual electron propagator with spin lambda. You might not see it, but it's lambda. Okay, so with these four propagators, we can then write down the simplest interaction vertices for this H1 Hamiltonian, because as you recall, we will have different powers of H1, so it's kind of convenient for us to write down each component of this. Later, when we multiply them together, we'll just use vertices in the Feynman diagram. There, as the diagram shows. So we know then, each will have one vertices. So with nth order, we have n vertices. Yeah. Then we draw the Feynman diagram for different orders. In the first order, we only have one vortex, and second order we have two, and third order we have threes. In the first order, we can easily write down the amplitude as follows. It is proportional to this, the expectation value of C dagger C minus 1/2. So the C dagger plus C dagger C is the first diagram A, because if you recall that we have this C dagger, this one, C dagger C here. And the second one is just minus 1/2. And the second order consists of, so for C, it has two Sions, so we have two Sions. And for D, we have one Sion and one Dion, So it's a spin flipping part. So for the third order, there are actually a lot of Feynman diagrams. I only choose one to show you, to illustrate you that it's actually kind of interesting. So in the third order correction, we have 2 cions and 1 dion. Okay, now let's take a closer look to the third order correction. So from the book chapter 4, we calculated the many electron Green's function. So and we get this form, where in the energy space we have 2 terms with 2 positive signs here, so the same sign. But since now we have this sion and dion operator here, propagator here, let's look at what sion and dion propagator does. So for t greater than 0, sion gives you a minus I over 2, sorry. And for t smaller than 0, it gives you plus I over 2. So basically flip the sign for t greater and smaller than 0, and d does the same thing. Because we have 3 terms here, each flip the sign, so then 2 of them will cancel them out, and in the end we will have a sign flipped. And after you do the Fourier transform, we will then have the sign of these 2 terms will be different. And it's actually this sign flipping that's causing the long 1 over t behavior in the Kondo effect. Let's look at the lower order terms, why they can't flip the sign. Just staring at the propagators, we can see. So for the flipping operator, I remind you, it is the sion times the dion operator. It flipped it twice, so basically it does nothing. And sion square also does nothing. So it does not flip the sign. And so it does not have, this kind of long 1 over t at lower orders. So it turns out that all higher order terms, the order greater than 0, exhibit this flipping of sign. And we can sum over all the higher order diagrams to get the T matrix. We observed that this T matrix actually has a pole at epsilon k equal to this, where you turn denominator goes to 0. And the Kondo temperature is defined as KBTK equals to epsilon k. Meaning that we have a singularity at the scattering amplitude. So basically it's saying that when t reaches tk, the scattering cross section will increase to infinity, which is impossible. So although this T matrix will give you a long 1 over t behavior, but it does not explain anything below the TK temperature. Therefore, the renormalization is needed. Renormalization is kind of complicated, so we will only illustrate or show the answer after this process were done. So for t greater than tk, we have this long 0.77d over t, which is a Kondo behavior. So finally we get the Kondo, we explain the Kondo effect of long 1 over t. Ooh. And for t smaller than 0, t smaller than the tk, we get this result. So you can do the Taylor expansion of, because this is a -1, you can do the Taylor expansion, so you get 1 minus this term. So basically it's a Fermi liquid behavior where you have the perturbative amplitude is proportional to t squared. And we can also determine the tk using this formula. Again, this is also given in the process is given in the papers here, where all the parameters are defined here. D is the cutoff energy, which is also the bandwidth. So let's then interpret this result. What does it mean? So initially, we know at temperature greater than Tk, we have this free local moment, meaning that we can treat our system's ground state as the Fermi sea. But as we approach to the Tk, this assumption actually breaks down. It is because that the correlation between this local moment and this our Fermi sea becomes so strong that you can no longer use local perturbation theory. In the end, when it reaches to the Fermi liquid regime, namely T smaller than the Tk, your local moment actually forms a bound state, forms a singlet bound state with the spin of the electron on that site, meaning that you no longer have this free local moment. Therefore, the perturbation, you cannot use the perturbation theory. So this explains why Anderson talked in his lecture. So let's see what he said. He said the best physics description of what happened is that at high temperature or high energy scale, the Hartree-Fock theory, in the Anderson model they used Hartree-Fock theory, but here we use Green's function, gives above is correct, and there is a free spin. But as the temperature or the energy scale is lowered, the effective antiferromagnet coupling between the spin and the free electron gas. So basically our initial local free spin and the free electron gas, this correlation, this coupling actually becomes a very large value. Eventually you cannot use the perturbation theory and become strong enough to bind an antiparallel electron to it, which is this this bound state, and becomes non-magnetic. Okay, great. So now we understand the whole process. This is the schematic temperature field phase diagram of the Kondo effect. We didn't discuss the x-axis. We only discussed the y-axis about temperature. So after we derived all these things and give you the result after the self-consistency calculation, we want to compare our model with the data. So on the left, we have the data for T below Tc. So the Tc is represented here. So the calculated Tc is around 16 Kelvin. And this Tc is from the experiment. So it's kind of, it's really in agreement. For this part, we expect to see a saturation behavior at T equal to 0, according to this, this formula. Indeed, we see a saturation at T equal to, when T goes to 0. And on the right, we have T greater than Tc, so the weak coupling regime. We expect these functions to behave like ln 1 over T. The lines, the curves represent the theoretical model, and the dots is the actual experimental data. So we can see they fit pretty well. So then I will discuss the universality of the temperature dependent of the resistivity. This is really interesting. So although we know for different materials with different coupling constant J, they will have different, they will have different Tc. But if we try to renormalize the T with respect to Tc and the rho with respect to rho 0, essentially it's this zero temperature resistance, then we get this function, right? And it seems like they all fit into the same line. meaning that this f is actually a universal, universal function. Meaning that, later if we have a new material, then we can also fit this material into these lines. Future of the Kondo physics. You might already realize that what we discussed before is all the works from 1980s, 1970s. They're actually, developed state of art STM study on the Kondo effect. So Kondo effect is a localized phenomenon, and so is STM, is a localized probe. So it's really suitable for studying Kondo. We can manifest the natural magnetic impurities onto the surface of metal, and then measure the density state on the impurity side. Just like the picture I showed on the right. The bottom layer is a couple layer where they kind of manifest these cobalt atoms on the surface of the surface. This forms the ellipse, and there is also one extra cobalt atom on the focal point of one of the focal point of this ellipse. The top layer is the DIDV spectroscopy. As you already know from the Ashley's talk, the DIDV spectroscopy is proportional to the density state of the surface. So we see two peaks here. Because it's also measured on the Fermi level, so these two peaks actually correspond to the density state on the Fermi level. So you might, in the first several slides that I showed you, there is a peak on the Fermi surface, and that is this peak when you add this magnetic impurities onto the metal surface. Quantum dot system is also really powerful in studying Kondo effect. So on the left we have a quantum dot system where we have this gate, and we have a source and drain. In the middle there is a quantum dot. They can trap the electron inside. So why is it so powerful? They can actually tune the gate voltage and change the electron that was trapped inside this quantum dot. So here, when gate voltage is increased, the number of electrons trapped goes from even to odd, meaning that there is a residual s equal to 1/2 created here in this odd side. So as you decrease the temperature from this orange line to this blue line, for the even, which means you don't have a residual spin, you actually decrease the conductance, meaning that you don't have a Kondo effect here. But when the spin is non-zero, is 1/2, when you decrease the temperature, you actually increase your conductance. So you see the Kondo effect. In the bottom, you have two pictures, conductance versus the TK, versus the temperature. So the right picture is the normalized picture to the TK. So you can see that it actually converts to one line, which is another experimental illustration of the universality function F. And with this, I would like to thank you for your attention, and please leave your question in the comment. I will answer them as soon as possible.